Permafrost refers to ground, soil or rock, that remains frozen for at least 2 consecutive years. It is primarily found in high-latitude regions such as the Arctic tundra and boreal forests. Beneath these cold, frozen surfaces lies an immense quantity of organic carbon, preserved for millennia in a cryogenic state. When frozen, this carbon remains largely inert. However, as global temperatures rise due to anthropogenic greenhouse gas emissions, permafrost thaws, and microbial decomposition resumes, releasing carbon dioxide and methane into the atmosphere. This process constitutes what is known as the permafrost carbon-climate feedback. It is a self-reinforcing loop. Warming causes permafrost to thaw, which releases greenhouse gases, which in turn contribute to further warming. The magnitude and dynamics of this feedback are critical to understanding the Earth's climate trajectory, but remain one of the major uncertainties in global climate modeling. Historically, estimates of the carbon-climate feedback from terrestrial ecosystems have focused largely on temperate and tropical zones. These regions store much of their carbon in vegetation and surface soils. But permafrost soils, although remote, harbor the largest single terrestrial organic carbon pool, estimated between 1,330 and 1,580 billion metric tons when including deep deposits such as Yadoma and thermokarst. These deep, frozen carbon stocks are stabilized by both cold temperatures and water saturation, making them highly sensitive to climate change. While Earth system models have begun to incorporate permafrost processes, they often lack sufficient observational constraints and can differ widely in their projections. As a result, there is significant uncertainty surrounding how much carbon will be released from permafrost soils as the climate warms, and how rapidly. In response to this challenge, Thawing et al., in the 2015 study, a simplified data-constrained approach to estimate the permafrost carbon-climate feedback, propose a straightforward, data-driven modeling approach. Their method integrates empirical soil carbon data, laboratory measurements of thawed soil decomposition, and projected changes in soil temperatures from climate models. By focusing on one specific mechanism, carbon loss due to increased decomposition following thaw, the study aims to provide a robust estimate of the sensitivity of permafrost carbon stocks to warming. This is a crucial step toward quantifying the strength of the permafrost carbon-climate feedback and improving projections of future climate change. To estimate how permafrost carbon responds to climate warming, Thawing and colleagues developed a simplified yet data-constrained modeling framework. Their goal was to focus on the large-scale carbon losses driven specifically by microbial decomposition in thawed soils. Rather than simulating the full complexity of permafrost systems, their method isolates one key feedback pathway and uses real-world data to guide the model's assumptions. The approach is built on 3 primary components. First, the researchers began with observed maps of permafrost region soil carbon. These maps incorporate detailed data about the amount and vertical distribution of organic carbon across different types of frozen soils derived from recent syntheses. Unlike traditional models that generate initial soil conditions through internal assumptions, this study starts directly from the observed carbon stocks. Second, they incorporated results from laboratory incubation experiments. In these experiments, soil samples from permafrost regions are thawed under controlled conditions, and scientists measure how quickly carbon is released through microbial decomposition. These data allow the authors to model how organic carbon decays over time once the soil thaws, using a simple 3-pool decomposition model that separates fast, slow, and very slow carbon turnover processes. Importantly, this decomposition is assumed to occur only when the soil is above freezing. The third and final component is the temperature data, how permafrost region soils are expected to warm in the coming decades. Rather than calculating temperatures themselves, the authors used soil thermal profiles from several established land surface models, which simulate how deep soil layers respond to projected climate change scenarios. These models provide temperature trajectories over time and depth, which drive the rate of carbon loss in the decomposition model. By integrating these three components, observed carbon stocks, laboratory-based decomposition rates, and climate-driven soil warming, the authors created what they call the Pink Panther approach. This framework allows them to estimate carbon losses across the northern permafrost region under two different climate scenarios. Without relying on more complex and often poorly constrained Earth system models. While this method deliberately omits many secondary processes, like vegetation changes, fine-scale soil hydrology, or abrupt thaw events, it offers a clear, data-grounded estimate of the long-term carbon release from thawing permafrost, driven by warming alone. The analysis conducted by Thawing and colleagues reveals that permafrost region soils are highly vulnerable to warming, with widespread carbon losses projected over the 21st century. The model begins with an estimate of current permafrost region soil carbon. These soils, primarily within the upper 3 meters, contain about 727 billion metric tons of organic carbon. This carbon is distributed across various soil types and depths, with large amounts found in peat-rich organic layers and in deeper mineral soils. In addition, substantial but less widespread carbon stocks exist in deeper eudoma and thermokarst deposits, though their contribution to near-term feedback is limited under gradual thaw scenarios. As the climate warms, soil temperatures are projected to rise and active layers, the seasonally thawed surface soils, are expected to deepen. This leads to increased decomposition and carbon release. Under a moderate global warming scenario, with an average temperature rise of approximately 1.2 degrees Celsius by 2100, the model estimates a carbon loss from permafrost region soils of about 21 billion metric tons. Under a more severe, unmitigated warming scenario, with a global temperature increase of around 3.4 degrees Celsius by century's end, projected carbon losses rise to roughly 57 billion metric tons. These losses are primarily from near-surface soils, where seasonal thawing is already occurring. However, the largest proportional losses occur at the southern edge of the permafrost zone, where warming leads to permanent thawing of deeper layers. In these areas, formerly frozen soils transition into talics, unfrozen ground that allows continuous microbial decomposition. Methane emissions, which are produced under water-saturated, oxygen-poor conditions, are also projected to increase. The study assumes that peat-rich soils remain saturated, and under warming, methane emissions rise by approximately 7% in the moderate scenario, and by about 35% under the more severe scenario. These increases add further greenhouse gas forcing, equivalent to roughly 10 to 18% more warming, due to methane's high global warming potential. Overall, the study finds that carbon losses scale nearly linearly with temperature rise, allowing the authors to estimate a sensitivity value. For each degree Celsius of global warming, between 14 and 19 billion metric tons of permafrost carbon are lost. This quantification provides a clearer estimate of how strongly thawing permafrost may amplify climate change. The findings of this study offer critical insights into how the thawing of permafrost soils may contribute to climate change over the coming century. Thawing and colleagues demonstrate that even with a simplified, data-constrained approach, substantial carbon losses are likely from high-latitude soils as global temperatures rise. One of the key conclusions is that the sensitivity of permafrost carbon to warming appears to be roughly proportional to the amount of warming itself. This implies that carbon release from permafrost is not only significant, but also predictable on a global scale if temperature trajectories are known. This linear relationship provides a practical tool for estimating climate feedbacks and integrating them into broader climate projections. Importantly, the study isolates one particular pathway of carbon loss, the enhanced microbial decomposition of soil organic matter in response to gradual warming and thawing. By doing so, it sets aside other complex processes, such as abrupt thaw events, changes in vegetation, fire disturbances, and hydrological shifts, that could either amplify or mitigate the observed feedback. While this narrow focus simplifies the modeling, it also means the results likely represent a conservative baseline, potentially underestimating the full scope of permafrost-related emissions. The authors also emphasize that the modeling relies on a number of assumptions, including fixed plant carbon inputs, consistent water saturation in peat soils, and no changes to microbial or soil structure over time. These simplifications are necessary for a scaling approach, but they introduce uncertainty about how closely the model trajectory will reflect real-world responses. Nevertheless, the strength of this study lies in its ability to anchor projections in observed data, using actual soil carbon distributions, lab-measured decomposition rates, and independently modeled soil temperatures. This approach helps to reduce some of the structural uncertainties that have complicated past efforts to model permafrost carbon dynamics in full Earth system models. Ultimately, the work highlights that permafrost carbon is not a marginal player in the climate system. Even gradual, widespread thaw can result in carbon releases large enough to noticeably amplify global warming. Including this feedback in climate policy and mitigation scenarios is essential. Studies like this one are critical because they provide transparent, testable frameworks for estimating long-term climate risks. As observational datasets improve and models evolve, simplified approaches grounded in empirical evidence will remain a valuable tool in understanding and planning for the role of permafrost in Earth's climate future.